In our last lesson, we had learned about the different types of filters. We talked about the finite impulse response filter and the infinite impulse response filter, and we outlined the difference between the two. We also discussed the different ways of implementing filters. In this particular lesson, we are going to discuss into a little detail the design of the finite impulse response filter. So there's several possible methods of designing the finite impulse response filters, which includes the Fourier transform method, called Fourier transform method. We have what we call the window method. We also have the frequency sampling method. And then we have what we call the optimal design method. So before we discuss the various methods of designing these filters, I will give an overview of what the finite impulse filters are. So we saw that for a finite impulse response filter, if you have your filter, you have the filter, then you feed it with an impulse input, then the output would be an impulse response, which is finite, does not go on forever. Because even the input signal, if it is an impulse signal, let's say we have delta n, it is finite. So the output will also be finite, as opposed to the infinite impulse response filters, where you feed the filter with an input delta n, which is finite, but the output would end up being infinite in terms of time, because some parts of it are fed back, so that even by the time you have removed the input, there would be an input to the filter and there would be an output to the filter, so that the response is considered to be infinite. So for a finite impulse response filter, we can consider the input-output relationship to be in the form of y of n being equal to the summation of the inputs from I equal to 0 to k, bi x n minus I. Of course, if we expand this, then you can see we'll have for I equal to 0, put I equal to 0 for the first one, I will have b naught x n because if you put 0, um, put 0 here, put 0, you get this plus b1 xn minus 1 plus b2 xn minus 2 plus up to the final one bk xn minus k. In fact, to make it even more clearer, we can choose a particular value of k. Let's say k is equal to 2. Then now the filter output will simply be expressed as y of n equal to the summation from I equal to 0 to 2 of bi x n minus I. And if I substitute the values, then I will have y of n equal to b0 x of n plus when I equal to 1, we put a 1 there, b1 xn minus 1. And when y equal to 2, put a 2 here, so that we have b2 xn minus 2. So if we do this, then such a type of filter, we can describe it as a three-tap filter. Because there are three coefficients to be determined. See, we have b naught, we have b1, we have b2. In fact, designing this filter involves determining this coefficient, determining the coefficients. The values of the coefficients will determine the nature of the output. And you can see that implementing such a type of filter can be a straightforward thing, because once you have the input, you multiply the input by b naught, add the delayed version and multiply by b1 plus another delayed version delayed by 2 is multiplied by b2 to get what the output is. And we can easily get the transfer function of such a filter. Because if, for example, you have this particular filter that we have described, then we are simply saying y of n is equal to b naught x n plus b1 x n minus 1 plus b2 x n minus 2. Then if you get the z transform of both sides, then we will have y of z equal to b naught x of z plus b1 x of z minus 1 plus b2 x of z minus 2. Or this can simply be expressed as x of z into b naught plus b1 z minus 1 plus b2 z minus 2. So that y of z over x of z would be given by b naught plus b1 z minus 1 plus b2 z minus 2. Let's have an example of the filters of our finite impulse response filter that has the values of the coefficients which have been determined. So I will have, let's say we have example So I have given the following FIR filter. Given the following FIR filter, y of n equal to 0.1 x of n plus 0.25 x of n minus 1 plus 0.2 xn minus 2. Determine the transfer function filter length, non-zero coefficients, and impulse response. So let's see how we would go about solving such a problem. So to determine the transfer function, we simply need to get the Z transform of both sides of the filter. So we have y of Z equal to 0.1 x of Z plus 0.25 x of Z minus 1 plus 0.2 x of Z minus 2. But we know that h of z is equal to y of z over x of z. So this means that the transfer function will be given by 0.1 plus 0.25 z minus 1 plus 0.2 z minus 2. So we have been asked to find the length of the filter. Actually, the length of the filter is equal to 3. The other way of looking at it is to say that it has 3 taps. 3 taps. And the non-zero coefficients are B0 equal to 0.1, B1 equal to 0.2. Actually, it is 0.25, sorry. I see there are 5 here. No, yeah, 0.25, fine, is 0.2. And B3 equals 0.2. To find the response in the time domain, we only need to obtain the inverse transform of this function, and then we'll be able to get the time domain response as h of n equal to 0.1 delta n plus 0.25 delta n minus 1 plus 0.2 delta n minus 2. So the transfer function of finite impulse response filter always have the constant term, and the other terms are raised to the negative or minus 1. That is, all the poles are at the origin, and the filter would always be a stable filter. And as I had said earlier, the design of these filters involve getting these coefficients, so that anytime we have an input, we multiply the input by the constant term, delayed versions by the other terms. Okay, so the design objective is to obtain the FIR filter coefficients BI such that the magnitude of the frequency response, such as the low pass filter, the high pass filter, band pass filter, or band stop filter are realized depending on what we want to do with the filter. And filters find wide application in all electronic systems, transmission systems, components we use for different purposes in our stalls everywhere. So in this lesson, we'll move and discuss the filter implementation or filter design through what we call the Fourier transform method. Remember, we have said these are all possible ways of determining, of designing our filters to achieve a given objective. And as we are going to see, the Fourier transform method is a very basic and straightforward way, in spite of some of the problems that it has, which is solved by resorting to the other design methods like the Windows method to improve certain aspects of the response of the filter, which is designed using the Fourier transform method. So we'll proceed straight away and discuss the Fourier transform design method of the finite impulse response filter. As a way of illustrating this design method, we'll use a low pass filter. And if we have a low pass filter, then already we know the response in the frequency domain. It has to be a low pass filter. And the low pass filter, we know that it will have some constant frequency. Then within the cutoff values, the amplitude of the signal is passed through the filter, while it is attenuated for any other frequency. So if we denote the cutoff frequency by omega c, capital omega c, that we usually use to denote the digital frequency, then what we also know is that the filter response is periodic. So that if this is what we want, this is what we desire, is the frequency axis, then it will definitely repeat itself. It will repeat itself. So that we can actually, if we were to continue plotting the filter characteristics to extend it to the other frequencies, then we'll have similar ones periodically, which we are going to illustrate in a few minutes' time. But for now, the mathematical definition of this filter would simply be that H, E, J, omega would be equal to 1 so long as the frequency lies between between 0 and omega c, and would be 0 so long as outside the omega c, or when omega c is less than omega. Okay, this have a 0 here. Okay. So this is the frequency response of an ideal filter. The frequency response of an ideal filter. So we have basically defined this region of our filter. Because if omega is greater than this omega c, then the response would be 0. But between this and this, the response is 1. And we have said that we can actually extend this drawing. We can extend this by having just have this. Yeah, we have drawn this. This is what we have. Need to be yeah, we have that minus omega c 0 there. We have pi, we have minus pi. So it repeats itself so that if this is 0, after 2 pi here, we'll also have the same. Here I have 2 pi minus omega c, sorry, omega in omega c minus omega c, 2 pi plus omega c. Omega, to write it well. Omega c. The same will repeat itself to on this side, 2 pi. I will have the same response here. Well, this is given by 2 pi plus omega c minus 2 pi plus omega c minus 2 pi minus omega c. Omega always in capital. So it's periodic. The filter response would be periodic. We want to, because the idea here is that if we know the frequency response to be this, what should be the time domain function? This would be equivalent just to getting the inverse transform of a function. If we have expressed this one in the frequency domain, what we need would be like getting the inverse Fourier transform of this, so that we get the time function and we get the associated coefficients. So if we borrow from the Fourier coefficients in the um, Fourier series expressed in exponential form, then we'll have h e j omega equal to this summation n equal to minus omega c of n e minus j omega naught n omega. And the coefficients c of n are determined from c of n equal to 1 over 2 pi. The integral from minus infinity. Here we don't need to use the infinity, it is periodic. So we just do for 1 minus pi to pi h e j omega e minus, no, not minus, sorry, e j omega naught and omega. The only change we have done here, if you compare to the Fourier series in the time domain, is that t will replaced by n. And of course, omega, the analog frequency, we have replaced by the digital frequency. And everything remains the same. And then we are also able to determine the omega naught, which is the fundamental frequency. The fundamental frequency, omega naught, is the fundamental frequency. Omega naught can be expressed as 2 pi over the period of the waveform. Over the period of the waveform, which would simply be omega naught equal to 2 pi over 2 pi is equal to 1. So this further simplifies our equation. So we have determined this, because what we actually need to determine are these coefficients. And at this point, we can also say that h of n, we can also say that h of n would be the c of n, what we want to determine. H of n would be the c of n, or what we call the desired frequency response. The desired frequency response. So that means what you'll do is that h of n that we want will be given by the integral from minus infinity, so from minus pi to pi of h e j omega into e j omega n. Okay, so this is very important. This is very important. Okay, consider a possible Z transform if we substitute E, j omega to equal to z to this function. A possible z transform associated with this function would be would be would be h of z equal to summation from minus infinity to infinity h of n z minus n. Okay, a possible z transform associated with this function, which of course will show that if we get the z transform, then we'd have the negative and the positive values. In other words, I will have something like this, plus h minus 2 z2 plus h minus 1 z1 plus h0 plus h1 z minus 1 plus h2 z minus 2, which implies what would actually come out with here is a non-causal filter. It's non-causal in the sense that even during the negative time values, the system already have outputs. So when we finally design our filter, then we have to see how to make adjustment for this, because the practical filter actually has to be a causal filter. So let's go back and then see how can we determine the coefficients of this filter. We have seen that we have the h of n equal to 1 over 2 pi, the integral of minus pi to pi e j omega, sorry, h into this e j omega n g omega. So let's see what is for n equal to 0, what we have. For n equal to 0, we are going to have, because we are going to put 0 everywhere, so we'll have h of n equal to the amplitude is basically 1. You put a 0 here, it becomes 1. So the integral, of course, we need to change. We can change so that on this side we have omega c. On this other side we have minus omega c. Because even though we are integrating between minus pi and pi, as you can see, minus pi and pi, values just start from minus omega c to omega c. So we'll have here 1 over 2 pi into negative omega c 1 d phi, which is actually 1 d omega, sorry, 1 d omega, 1 d omega. Which is actually equal to omega c over pi. So this is actually h0. For the other values, h of n would be equal to 1 over 2 pi, the integral from minus omega c to omega c, e j omega n d omega. This is equal to, if you integrate this, we'll basically get e j n omega over 2 pi j n, then substitute from minus omega c to omega c. And this will give you 1 over pi n into e j n omega c minus e minus j n omega c over 2j, which we can simplify to the sine of omega c n over pi n. So the desired impulse response of the filter, we can sketch it. We can sketch this desired impulse response of the filter. You can see this will take the shape of a sinc function, so that if I sketch the desired input response, then what I will have will basically look like this. I will have a higher value at n equal to 0, followed by subsequently smaller values as the frequency increases. The frequency increases. So, and not as n increases, sorry. Then we'll have that then they'll continue being progressively small as we move on. The same to this side. They continue being progressively small. So that the filter, finally we need to truncate the filter. So that maybe we just have these coefficients and do away with these others. But on this one that we have chosen, remember 0 is here, we have negative values, we have positive values. Then maybe we need to, once you have determined that this is the desired part of the filter that we want, then we need to shift it so that we don't have the non-causal parts of this filter. That's one thing that we're going to see, that how are we going to shift the response so that we only have the values that correspond to the positive time. So we have seen that what we saw up is that eventually when we come up with our filter, we will have the response in the form of, h of z equal to hm zm plus h1 z minus 1 h0 plus h1 z minus 1 plus hm z minus m. But now we would have to determine the coefficients from here, so that eventually we want a shift. We want a shift so that our h of z is in the form of b naught plus b1 z minus 1 plus b2 z minus 2m, where we create a delay operation given by bn being given over h into n minus m, which is just a shift that I was describing before. So we'll see this with the help of an example on how we can design this filter. So, but up to this point in time, we have come up with two important expressions, which are, are available in books. We can always use them. We can always use them if we need them. Um, we had there to look for them. We have the functions. This, yeah, this function, very important. The fact that what I've said is valuable in the books is the fact that for a low pass filter, for n equal to 0, the coefficient is given by omega c over pi. For any other value of n, we have h of n equal to sine omega c n over pi n. So these are even available in the books. We can always use them for the design. In this case, this is for the low pass filter. But we have values which are be derived for the high pass filter, for the band pass filter, for the band stop filter. And we can use all of them to be able to design the filter. And by designing the filter, just as I said before, the issue is about determining the filter coefficients. So let's have a look at an example to illustrate how we can obtain the filter coefficients of desired characteristics. Then part B, we have determine the transfer function of the filter. Determine the transfer function of the filter and difference equation and different equation of the designed FIR filter. So let's see how the solution of this equation go. You would notice that it is a straightforward design because most of the times you not have to prove the equation for the transfer function of the filter. So we'll have, for example, mm, let's have our solution. So we have said the design equations, which most of the times will be provided and you may not need to derive, would be as follows. And we have h of n equal to sine omega c n over n pi for n not equal to 0. So this will be our design equations for the low pass filter. If it is, for example, a higher pass filter, any other filter, then we have to be provided for. So the first thing to determine is to determine the normalized cutoff frequency. We have been given the cutoff frequency, but we need to determine the normalized cutoff frequency. We have omega c. Actually, um, what happens that we need, how do we get the normalized frequency? We divide the frequency divide the frequency divide the frequency by the sampling frequency f of s, that is omega c. Remember, omega is equal to 2 pi f, of course, but now this is the normalized one. We have 2 pi f c over the sampling frequency. Or the sampling frequency. So we'd have 2 pi times 800 over 8,000. The other way of looking at it is that we have normalized this, then we have multiplied by pi to get the the omega. Since omega is given by 2 pi times f, we can get the normalized value of this by dividing the cutoff frequency 800 by 8,000, which is the sampling frequency. So this gives us a frequency of omega c equal to 0.2 pi radians. Therefore, we can go ahead and determine the coefficients. We have also been told that it is a 3-tap filter. The filter is a 3-tap filter. So this means that 2m plus 1 equal to 3. Therefore, H naught equal to the magnitude of the filter response as n equal to 0 is given by omega c over pi, which is equal to 0.2 pi over pi is equal to 0.2. Then for the other values, we have h of n equal to sine omega c n over n pi is equal to sine 0.2 pi n over n pi. So we'll have h of 1 equal to sine 0.2 pi times 1 over 1 times pi, which is actually equal to 0.1872. Remember, the filter response is 3 taps. So if you go back and check, then we saw that what we basically have, we have an amplitude at n equal to 0, we have a value. We already have that. The amplitude 0.2. Then we have a value there, a value there. When we have this h of 1 to be this, by symmetry, we also know this. By symmetry, we also know this. Because we can say, using symmetry, h minus 1 equal to h1 is equal to 0.1872. This one is equal to this one. You also have this. So we have the coefficients. But what we are discussing is that the filter out to be non-causal. So we need to shift this. So that is the bit that now remains. That we shift by, can see TC, if yeah, we shift using this. Bn equal to Hn minus m. That is Bn equal to H into n minus m. So this means B naught equal to H into 0 minus m. Remember, m is 1. m is 1 because we had the filter coefficient 2m plus 1 equal to 3. If you solve for this, m equal to 1. So we have b not equal to h into 0 minus 1 equal to h minus 1. It is okay because we are saying if you look at, just look at this one here. That this one we saved it so that it goes here. So we are saying b 0 equal to h 0 minus 1 equal to h minus 1. Like the first coefficient would be which is equal to 0 and 1872. b1 equal to h into 1 minus 1 equal to h of 0, which is equal to 0.2. And b2 equal to h into 2 minus 1 equal to h1 equal to 0.81872. We are simply saying we have shifted this. So we have the filter coefficients, and that is where the design ends because we have written the filter coefficients. So we can easily write down the filter coefficients in part B of the question by saying we just have the transfer function. The transfer function is achieved as follows. The transfer function is achieved as follows. I have h of z equal to 0.1871, which is the b naught, plus 0.2 z minus 1 plus 0.1871 z minus 2. So that is it. And if I want to find the time domain function for this, then what I need to do, you know that h of z is equal to y of z over x of z, which is equal to what I have there, 0.1871 plus 0.2 z minus 1 plus 0.1817 z minus 2, or yz is equal to 0.1871 xz plus 0.2 z minus 1 xz plus 0.1817 xz z minus 2, from which we obtain the differential equation y of n as a result of getting the inverse Fourier transform as y of n equal to 0.1871 x of n plus 0.2 xn minus 1 plus 0.1871 xn minus 2. So we have designed our filter. We have been able to get the transfer function. We have been able to get the difference equation, and we can choose any of the implementations that we had discussed in our previous lesson to implement this filter. So in our next module, we are going to discuss some of the problems that such a filter which is designed using this method has, and how this can be solved by using the window method.